but okay, let's do it. Okay, so thank you for invitation and giving me this opportunity to give you this talk. This is talk based on my recent draft. So well, I think everything is okay, but if you find some mistakes, then please give me the feedback. Okay, so I will be talking about inverse problem of the calculus of variations in some nice framework which is called functional exterior differential calculus, which more or less sometimes I invented, but also there was some hints about this before my work. Okay, the plan of the talk is as follows. So first I will introduce this problem of inverse problem of the calculus of variation. Then I will at least try to convince you that there is some nice calculus which is similar to differential exterior forms, which can be used to solve this problem. Then I will present some very old theorem, which is called Helmholtz-Weinberg theorem, which basically is the Poincare lemma in functional way. So everywhere is Poincare lemma. So if you remember my previous talk here, then I try to convince you that Poincare lemma can be used to solve all nice problems in physics. And that's the next step that I will try to apply Poincare lemma to variational calculus. So everything is Poincare lemma in physics, more or less. Okay, then I will present some basic examples of how to apply this exterior calculus, this functional exterior calculus to some well-known examples. But it will convince you that everything works at the basic level. And then I will present some kind of problem which can be used which is called multiply problem. So basically you multiply equation by something. If equation is not variational, then you can save the day by multiplying this equation by some constant, and then maybe it becomes variational. So I will present some nice examples, and finally I will present a nonlinear version of this multiplier problem, which I think it is the first time somebody formulate it, so maybe it will be interesting. At least at my current level of the knowledge, I think it's the first time. And you can solve it effectively using this functional exterior calculus. And after that, I will give some summary and literature just for interested people. Okay, so let's start with description of this inverse problem of the calculus of variation. So what's the problem? So we have a system of ordinary differential equations. So equations can be nonlinear. So we have the set of this equation, this epsilon I, which I runs from 1 to n. And assume that this equation is second order. So we have x dot, and x two dots. And this equation, because it's equation, so it's equal to 0. So the question is now, is this equation or are there these equations variational? So that's another question which is equivalent, that if there is Lagrangian, that you can derive from this Lagrangian Euler-Lagrange equations, which are exactly these original equations which you get. That's the basic formulation. And a solution for this problem was known very long time. It was derived a very long time ago, and I think by Helmholtz, because here is his name. But sometimes in mathematics and physics, people use different names for discoveries. So anyway, these are called Helmholtz conditions, and there is some system of partial differential equations in this case, which if you plug these equations into the system and you get that everything is okay, then you have proof that these equations are variational. So that's the standard way. Of course, yes.
Yeah, of course, there you have to say that you could still rewrite the equation, and then this test, Helmholtz test, would not be, I mean, sufficient.
Well, yes. So this is yeah. So the problem with this test, you're right, is with this test is that you get equation and you don't modify it. So it is in this note. So Helmholtz conditions can check variationality only for equations as they stand. So you don't modify these equations after plugging it to Helmholtz conditions. But it can be like as you suggested that if you plug these equations into Helmholtz conditions, you get that they are not variational. So these conditions are not fulfilled. But after some small change, you can plug these changed equations, and you get that these equations fulfill this Helmholtz condition. So it's
that could happen at least.
yeah. It happens a lot. So I will show even one example of this, which concerns this harmonic oscillation with damping, and this is a very nice example of this phenomena. But I agree that they are not very handy, I would say. Okay. Okay, sorry, some glitch. Okay, so Helmholtz conditions are working. Well, working, not working, but generally there are some conditions for checking this. But I'm usually a very lazy person, and I don't remember such conditions. Well, I cannot memorize it very nicely. So I try to find some other approaches to check this variationality, which is of course equivalent or more or less equivalent to these conditions. So the question is, what if you are too lazy to remember these conditions? Because I presented these Helmholtz conditions only for second order differential equations. If you go to third order, then this equation starts to be bigger and bigger. I mean Helmholtz conditions, so it's mess. Maybe there is another approach to checking variationality, which based on well-known tools from differential geometry. I mean tools in the sense of exterior derivative or some kind of differential forms, but in a very abstract or rough sense. And so yes, that the answer is yes, and this answer is exactly functional exterior calculus, which I now present. Okay, so let's dig into this exterior calculus on functionals. So the setup is as follows. Let's consider some kind of fiber bundle. So A is this whole total space. Sorry, M is here a base manifold, pi is projection, and typical fiber is W. And now, not this direction. And now we are interested in sections of this fiber, which the set of this section or space of this sections is called gamma of E. So we have functions from M to E. And now we construct a jet bundle on this bundle. So roughly speaking, you add to this coordinates of E more coordinates, which represents derivatives. So on the base manifold A, on this bundle A, the coordinates are XA and U. U are these coordinates of the section of A. And now you add some additional coordinates, which are here xi, u, and ui, where index I denotes multi-index. And well, in more concrete way, if you have some function which is defined on this jet or prolonged to this jet, then well, I denoted jk of phi, where k is then denotes how many these levels of differentials you have to add as coordinates. So coordinate xi acting on this jet function simply takes the coordinate on the base manifold. So coordinate of the point P on this manifold, where phi is defined at the point P. You coordinate u acting on this jet function gives you simply the u at this point, and coordinates u with index multi-index I acting on this gives you simply the derivative of this function on the jet manifold. So basically, say these coordinates are derivatives, or something which after restricting it to this say a prolongation of the function gives you derivatives, because there is some bigger structure. But anyway, in a very rough sense, the new coordinates on the jet space after a part of this a coordinates, so x and u, are derivatives, or something which can be transformed to derivatives in rough sense. Okay, so that's the idea. So we add these new coordinates. And now we can define a Lagrangian or something, some function on this jet space. Oh, just one more thing. So here k is some fixed number, but generally it's not defined well. So in the sense that sometimes you need bigger k, sometimes you need lower k. So the safest way is to start from k equal to infinity and then restrict your jet space to some finite number of these derivative coordinates. It depends on how much derivatives you need or you want. But anyway, you can define a Lagrangian, which is function on this jet. Generally it's the volume form or something which is proportional to volume form on the jet space. So L is a function which depends on this jet coordinates times dx here means the volume form. So it is something which is proportional to volume form, but with coefficients which depends on this jet space. So in physical applications, it's something like Lagrangian, which depends on x dot, which x dot is this first jet coordinates, x2 dots, x3 dots, and so on. As many as you want these derivatives, which are in jet space new coordinates. So this is function which takes this point in jet space and map it to the volume form, or something which is proportional. Yeah, please.
I guess you should just say that it's here you're actually doing. I mean, you're considering also field theory, so not just dots, but derivatives with respect to space time. So, time on your first slide now is replaced by space time.
Yeah, sure. So generally, this x dot and so on is in the case of the mechanics when you have one-dimensional, let's say, field theory. But generally, the t is replaced by x's and x is replaced by fields, so some phi or something else. Yeah, you are right. Perfect. So you are very attentive here. Nice. Okay, so now if you have this Lagrangian form, then you plug it into integral. So you integrate it and you get something which is called functional. So functional takes this jet point in the jet space and evaluates. Well, it's not exactly like this because you have to pull it back along some concrete section of this jet and then integrate. But generally, it's functional is something which takes some holonomic section of this jet, which means the prolongation of the function from the bundle to the jet space, and calculate some number. So generally real number, but it can be also some complex or other valued like spinor value. But generally, in physics, we use scalar Lagrangians, which are numbers. And now the basic assumption in physics is that if you have functional which is action, so it's integral of the Lagrangian, then you search for stationary point of this Lagrangian and you get the equations of motions, which gives you as a solutions the trajectories of physical system. So in functional way, this is called so we have to find some kind of derivative of this functional which should vanish, and if it vanishes you get the conditions for the extrema of this functional. So and this derivative is called Gatu. I don't know if I say it correctly, but this is this guy, and it's
I think you say it correctly.
Yeah, okay. Yeah, my French is not good, but I think yeah. So generally, it's something like a gradient in the case of normal functions. So This df is this Gauss derivative evaluated at point v and at vector eta, because derivative generally is a linear function. So it's this vector eta, which is the point where it's a vector which show you in which direction you go to and in which direction you change something. And phi is the point which show you at which point you check this change. So it's defined by, for functionals, it's defined the same as for ordinary derivatives for functions. So it's limit of epsilon tending to 0 of this form. And eta is here. So epsilon is some control parameter which tends to 0, as in standard calculus. So if you compute this, then you get something like this. So it's in linear change in eta. So you for example, extract this change and cut or kill because of this limit all terms which are higher than epsilon. So they are epsilon square and so on. So after that, you get linear change in this term. And it's something like this. So, oh, sorry, I changed notation. So instead of f, there should be L. So here should be L. So df over du. U is this coordinate of the jet, and here is eta. Eta is this change vector, or vector of change. And then there are du over dl over duk. And here is derivative with respect to xk of eta. Okay, so you get linear change in this eta. And so we have something like this. This is, I rewrite it again. But so after that, the standard procedure is to make integration by parts. So you take this total derivative and pull it by integration by parts here on this term. And you assume that the boundary term vanishes. So that's the standard, and you get precisely Euler-Lagrange equations. However, we don't have to do it. Well, if you want to get Euler-Lagrange equations, you have to do it. But let's stay at this formula and don't do integration by parts. Instead, let's look on this eta and these derivatives, total derivatives of eta. So let's construct some vector in jet space which contains these variations. So we construct a vector v which depends on this eta, and it's eta times du plus its prolongation. So it's total derivative of eta times dui, and this k is which restricts this the size of this index is fixed. It's some finite number, but it's large enough to accommodate these higher derivatives in this Gauss derivative. Okay, so we have something like this, and now let's assume that we define something which is called here delta ui, which after inserting this vector v pulls out from this vector the term which is in front of this dui, so di eta. It's something like ordinary derivative, well, exterior derivative, but or one form, but I denoted it here by not by d but by delta, because it depends. Well, it is related to functional. So later it will be very important that they are functionals, not jet spaces. But generally at this point, you can also write d instead of this delta, and it will be properly defined one form on the jet space. But soon it will change. So that's why I use, instead of d, I use delta. And moreover, you have following property that if you have delta of uk, where k denotes the size of this derivative or the jet coordinate, you can take this k in front of this delta by writing here total derivative with respect to k on delta u. You can check it by simply pulling, by simply feeding this both sides by this vector v and compute everything. Then this is exactly the equality on these eta coefficients. This is some abstract notation, but after feeding this stuff by this eta by this v vector, then you get proper equality, I would say. So we start from this concrete integral, which is evaluated to real number, and starts to make it some kind of operator, not something which can be evaluated easily to real number, just to be unevaluated formal expression. And let's see what happens. So now we are ready with all these definitions to formulate this functional exterior differential. So first, because, for example, here you have integral sign, and in each part you have integral sign, because that's how these functionals are defined by integrals. So maybe we don't want to write this integral each time we write this integral. So first simplification is to forget about this integral. So if I write delta u, for example, wedge delta ux, then I mean that there is integral sign and integration is over the variable which is inside this functional. So for example, here with dx. Okay, and now, so this is only something like Einstein summation convention. So instead of writing sums, you forget about this and sum over repeating indices. Here, you forget about integral sign, and there is implicit integration over the implicit variable on this base manifold. Okay, so now let's introduce our main actor, which is called functional exterior derivative. It is the same as normal derivative, but in terms of functionals. So I call it rho, well, because the delta sign was reserved for variational derivative, and this is more general construction. But in some cases, it's exactly variational derivative, but they are special cases in which this is equal. But generally, there is a functional exterior derivative, not variational derivative. So it is defined as normal derivative. So we have a derivative with respect to the jet coordinates, time this one form in functional way, which I called here delta u k, and summation is over k, up to some higher index. Okay, and now we can write this, well, the functional exterior derivative acting on this f, which is sorry, it was before that, which is this functional. So it's functional on the jet space. In our notation is something like this. Of course, I forget about integral sign, but we omit it. So that's our agreement, that we forget about integral signs. So here is everywhere integral sign, which is not written explicitly. So
sorry, can I ask?
Yeah, sure.
So what is sort of the map that this derivative acts on? So it takes functionals and returns also a functional, or it returns a number?
Yeah, no, it returns something which can be evaluated to functional. So if you write here integral, then this term is meaningless unless you supply it by some vector, some variational vector. So you, instead of this delta ui, you substitute like it's a good question. So first you have to supply this delta ui by this vector v, which is your variation. So it points the direction in which you want to change this functional. And for example, you can rotate, or you can point some function just to change it, and so on. Anyway, first you have to plug in this vector, this variational, some special variational vector to this integral. Then you have to pull it back to the base manifold from the jet space, and then after that you have to you can integrate it.
Okay.
So this is abstract notation. So you start from maybe it's a good point. So first you start from this equation, which can be evaluated to some strict number, like real number, because it's integral of some functions, and all these functions are given. And then you forget about this eta and says that you introduce instead of these eta forms, and if you plug into these forms this variational vector, you get this eta. So this is the first step. The second step is that you forget about integral sign, but it's only cosmetics.
Right.
And after that,
Radek, you should probably also say that your functional should be local. So your functional should be an integral of a Lagrangian form. Yeah.
Once again?
So you're talking about local functionals.
In the sense that this U is some open set of
no, in the sense that that, for instance, you can write your functional as an integral over something that depends only on the implicit, the independent function x, not two independent functions.
So
the point that there is a local. I mean, physicists would say that action only depend on one space-time point at the time, not two space-time points.
Exactly. That's the implicit assumption, but it's usually it's valid.
In physics we call that a local functional.
I know this, but I assume that's the case. But you are right. So sometimes these non-local functionals which depends on many points are better. For example, in QCD. But here we are in this say standard setup. Right. But it's a good comment. Yeah, thanks. So. Yes, so we have this say formal thing for formal expression, which resembles a bit of some kind of exterior derivative of functional f or function f, if f would be function. And now, now how to connect it with variational derivative? So here is this variational derivative, which can be written as a d delta u. So in this, of course, there is integral sign which is not written. So this is this Euler and Lagrange equation times delta u, and this delta u is always, or in many cases, substituted by this eta function, which is variation. In this case, it's one form which takes variational vector and substitute here this variation. And this is exactly, this is sometimes written as here, but in the full form, it's something like this. And what's the difference between this 13 this equation and 14? So the difference is that this in 13 equation, there is the dependence on higher jet coordinates. So this is, say, not integrated by part version of this 14th equation. Okay, so this 14th equation is proportional only to delta u, or to variation with respect to a function. But this 13th equation is dependent on the variations of derivatives. So the variation of the derivatives can be arbitrary in some sense. Of course, we use this variational vector, which is prolongation of this base vector. So they are not independent, but generally you can use this 13 equation as more general, say, approach to variation, like higher variation or variation in higher derivatives. It's well formulated in terms of jet spaces. There is analogous, say, definition of this variation. But it's not the same. Well, it's similar, but not the same as here, because here you have also integral sign, so it's not say a precise definition, but only some formal expression. But this formal expression is very useful because. So maybe one point more. So generally you have this functional exterior derivative, which are denoted by rho. And in some special cases, when you integrate by parts or these total derivatives from this delta ui term, then you get a variational derivative, which has dependence only on the variational function, so delta u, not its higher derivatives. So that's the difference between these two. So this notation is more say general, and you also see why I choose this rho for this derivative, because it's inverse of in the sense that it's flip of delta. Okay, so that was some kind of joke, but anyway. This idea is not new, but it's not well, I would say, presented even in physics books. But it's very general and it's very simple, so it should be presented. But so first I started to develop it myself. Then I unfortunately find out that somebody already did it, but only for my luck, only for this derivative, only for variational derivative, not for this general derivative. But they're almost equivalent up to integration by parts. But yeah, I was safe. I was happy that nobody find it out. I will present some sources about this variational derivative treated as an exterior derivative at the end. However, what I did was to extend all this notion of functional exterior calculus to the jet space, or something which resembles jet space. And then, sorry, I connected with homotopy formula. Homotopy formula was also known for variational derivative, but I extended and connected with some of my previous works, which I presented also here. There is very deep reasoning. When you connect it, there is deep reasoning what is Lagrange, which I present you soon. And also apply this to solve the inverse problem of the calculus variation very simply without remembering any Helmholtz conditions, which are quite complicated. So I will try to convince you that everything is okay here. And this approach works. So how it works? So this is a very simple example. We have something. Okay, so we have this expression mu xx delta x, which means that there is also implicit integral. So you write integral and integrate over dx, because x is this variable on the base manifold. So this expression means what is inside this bracket, and this is not a single expression. Because if you assume that these variations vanish at the boundary, then you can integrate by parts many times. So this form is, in the sense, it is an equivalence class of all expressions which are equivalent by integration by parts. So this means that this original expression, one integration by parts, so x goes on this variation, and also 2 times integration by parts. So after 1 integration by parts, you get this minus, and after 2 integration by parts, you get minus minus, so it's plus. So if you write the integrals here, then you get what you have in standard calculus variations. So that you have to remember that there is always integration which is not written. Okay, so this is our basic expression for some kind of, say, uxx equals 0 is our equation, which we consider. And now we apply this functional exterior calculus to this term. So it is written here, and it is, again, equivalence class of sorry, there should be delta. So delta uxx wedge delta u, or minus delta ux wedge delta ux, and this is 0 because of antisymmetry, because the antisymmetry kills the terms which are multiplied by wedge and are the same. And here is delta u wedge delta uxx. So it's simple, say, differentiation as in the jet space. But of course, there is this integration sign everywhere. And after integration, well, if you put integration, these equations are, or these expressions are still meaningless until you plug inside this delta u or delta uxx this vector v, variational vector. And after that, you can compute it to some number. But before that, you cannot. It's only formal expression, but very useful. Okay, so. So you take this and you can integrate by parts, and of course you can do this exterior, say, differentiation, this functional exterior differentiation. Okay, so now we are ready to rewrite this inverse problem of the calculus variations using, say, Cartan way, which means that we have some kind of exterior forms. We have exterior derivative, or some kind of, this, and we can try to rewrite this problem in terms of this antisymmetry and exterior derivative, like in Cartan original ideas. Okay, so assume we have a system of equations. So AU alpha on U is this field equals to zero, and we construct Euler form, and it's standard name for this. It's not my name. It was invented in this exterior calculus for this the variational derivative. So Euler form is a sum of these equations times delta U alpha. Well, U alpha is the field. So you have many fields like U1, U2, and so on. And delta U alpha are variations, or in the sense are one forms of this variation times these equations. So there is implicit sum. And now the question is so we have equivalent questions. The first one is the basic one. So if this equation is Euler-Lagrange one, so that's the formulation of inverse problem of the calculus variation. The second question, which is equivalent, is if this Euler form is equivalent to derivative, functional exterior derivative of some functional, some zero functional. So now we have access to the exterior derivative. So we can say that this is variational if there is some action functional which functional exterior derivative exactly this one form, this functional one form. So that's the one step further to this Cartan way of living, I would say. And so the reformulating this, you have the following. If this functional one form is exactly exterior derivative, functional exterior derivative of some functional f. So we don't know this. We have to formulate the conditions for this. But I hope you now flash the light in your heads that this is exactly what, in terms of standard exterior calculus, is about. The Poincare lemma is about. Yes, so this is exactly the question which is in Poincare lemma, but in terms of standard functions or differential forms. So our way is to find some analogy of this Poincare lemma in the field of functionals, and if you find it, then we can apply this to this exterior functional exterior derivative and solve the problem. So check if something is variational. Okay, and the question is if such functional analogy exists, and the question is yes, because otherwise I wouldn't present it here, and it's called Helmholtz-Weinberg theorem. Well, I call it functional version of the Poincare lemma because more or less it is this theorem. It depends. I don't know if Helmholtz was living before Poincare or probably after. So maybe Poincare was first, but Poincare doesn't consider functional analysis. So this is the theorem. It is from the book of Weinberg. It's a very nice book about functional analysis and inverse problems of finding primitive functions functional to get to derivative form. So the theorem is very simple. So we have some A operator which operates between A and A star. So A star is dual space, and A is a real Banach space with some norm. Of course, Banach space must have some norm. And now A has linear Gauss derivative, which is denoted by dA, which depends on the point in this space, on this Banach space U, and this vector which points which direction you compute the derivative. And say this Gauss derivative is defined in some ball of radius r. Then if the functional dAu which is evaluated on two vectors h1 and h2 is continuous at every point of d on this domain, well, it should be probably u. U. Then the A is because we assume that A is some kind of derivative, then we want to integrate this A to get this primitive for the A. So if we, so that's why we evaluate this dA on two vectors, h1 and h2, because we treat it as the second derivative, and second derivative is linear function, well, bilinear functional. So we plug here two vectors and evaluate this, and check if we can switch the order of h1 and h2. If these two ways of calculating this expression are the same, then of course this A is symmetric operator, and from this you get automatically that A has potential. So A is derivative of some potential, some functional, which is so you have some potential, you take a Gato derivative and you get A. And this is exactly the same as the content of Poincare lemma. Maybe just I will explain you in this lemma in very simple way. So it's the same as Schwarz lemma for derivative in Rn. So assume that you have Fa, which you want to be some derivative of some function f. Then, of course, if you make another derivative of f, then using the symmetry of the second derivatives, you get that fj, the dfj over dxi is dfi over dxj. But you know this because you know that fi is d small f over dx. If you don't know it, then you have constraints that if this is true, then probably f is this derivative. So that's what this Poincare lemma or Weinberg lemma or this Schwarz lemma or every lemma is about. So you start from some set of functions or operator fi. If you check this condition 22, and if it's okay, so this ij indices are well, this expression is symmetric in ij indices, then it means that at least locally, as Klaus said here, because everything now is locally, yeah, the assumption is that, yeah, about locality, the assumption is that you must be in some ball, and ball is, well, generalization or less general than a star-shaped set, which is assumed by Poincare lemma. So all considerations are local in some ball. Here, or star-shaped set. So if you have this condition 22, then you are safe to say that this f large fi is exactly some derivative of some functions f, which is in terms of Weinberg called potential for this f large f. So that's more or less the content of this Weinberg theorem, but of course in functional way it's more complicated, but generally it's or on simple terms, it's exactly commutativity of the second derivatives. That's more or less. And Poincare lemma is exactly the same. The commutativity of the second derivatives, but on the manifold. Okay, and
can I ask?
Yeah, sure.
So in this example, would this be a sufficient condition, this commutativity? Because to me, naively, it seems like it's just a necessary condition, but it doesn't prove that your f is a derivative of something. It just
precisely. Very good question. Yeah. So additional condition is topology. So topology enters in this assumption that we are in the ball, or generally we are in the star-shaped set, which means that we have a set which has center, and you can homotopically shrink this set to one point. So there is a homotopy which takes all the set to the one point. That's the topological assumption. And if you know this, then it's sufficient and necessary. Okay. Otherwise you don't have this. You have this only locally in open set or in star-shaped.
I mean, standard. The way, I mean, the direction you ask about, that's what's Poincare lemma. The other one is trivial.
Yeah.
Okay.
Yeah, precisely. So, but well, if you goes to Euclidean space, then Poincare lemma is exactly this one, because Euclidean space is contractible. So topology is the topological conditions is automatically fulfilled. Yeah. Okay. And in the course of this proof, well, of course, you can also prove, you use the same argumentation for this proof. There is a formula for this inversion of this exterior derivative or this differential. So it means that this potential for the operator A from the Weinberg theorem is A of u equal to A of u0, where u0 is the center of this star-shaped object or this ball, and the homotopy is from t to u0 plus t u minus u0. So you shrink everything to this u0 point, and this is the center of the homotopy. So this potential is defined up to this center. So this is the value of this potential at the center of the homotopy plus some integral of A evaluated at this homotopy times u minus u0. So vector from u0 to the point at which you want to evaluate this potential times dt, so times measure. And that's the general formula for inversion of derivative, or in terms of functional analysis, in terms the Gattau derivative. Okay, so we have this Helmholtz-Weinberg theorem, more or less, say, understandable. Of course, I didn't present the proof because this is not about the gore details, but I hope you understand more or less what's the mechanics of this theorem. So now we try to reformulate this theorem from functional analysis to this functional exterior calculus, which I presented you before. So this is the reformulation. So assume that we have one functional form f, which depends on this delta u or this variational one forms, and assume that it is closed. So if you take functional exterior derivative on f, you get 0. And of course, you have to assume this topology. So you are in the star-shaped neighborhood of some center u0, of section of some bundle. If this form is closed, because this rho acting on f is equals 0, we call this condition closeness of this one form f, then this Weinberg or functional Poincare lemma say that it's functionally exact, which means that we can locally inverse this exterior derivative to get 0 form or functional or action, which gives you after differentiation this one form f. Well, in simple in equations, it means that there is some g. This is this action functional, which is defined by g of 0. This 0 is exactly this term up to which this potential is, or this action is defined. This it depends on the center of the homotopy plus some homotopy operator acting on this original functional, and this homotopy operator is rho up to this star-shaped set. And now this g of u0 is some constant because it's 0 functional evaluated on some specific solution or some specific function, and g is functional, so functional evaluated on some function gives you some, say, real number. So this is only a number, some constant, and this homotopy h can be written. This is exactly this homotopy is exactly this part with integral, but rewritten in some, I would say, maybe not smart, but some standard way, that you take this integral over dt and you insert this vector k, which is exactly the jet prolongation of this u minus u0, which is here is u0 plus t u minus u0, and this part. Because this f can depend also on jet coordinates, so you have to plug in also higher derivatives, so prolongation of this u minus u0 inside, and then you evaluate it on homotopy, and after that you get the same formula as this Weinberg formula for functional analysis, more or less. So we have one-to-one correspondence between these functional analysis notions and this functional exterior calculus notions. So we can play now because we know that we can locally solve our problem. So, okay, so maybe one more comments about why this works. if we have second derivatives, say we are in Euclidean space, and so now this second derivatives commute. So the first derivatives in the second derivatives commute, and if we multiply it by something which is antisymmetric in this in indices I and j, then obviously it is 0. So because contraction of symmetric and antisymmetric say tensor or symbols are automatically 0. So that was original idea of Cartan, I think, that antisymmetry kills all symmetric terms. So if this is killed by multiplying by antisymmetric term, then it is exactly the Poincare lemma, I would say. So all the play is that the second derivative is symmetric, but if you multiply it by something which is antisymmetric, then you kill it. So what is left is this abstraction given by antisymmetry of this switching of a and j in this second derivative. Because not always second derivatives, the first derivatives in second derivative can commute. Sometimes they not, if function is not not too smooth, I would say. It is Schwarz lemma in standard analysis. But if you multiply this derivative by this antisymmetric part, then you see what is left, and what is left, it's abstraction to make this derivative or this antisymmetry to be 0. This it is this abstraction term which prevents you to apply this Poincare lemma. So that's the idea. Maybe it's very basic, but I wanted to make it clear because it's very, very center of all these physical applications. Okay, so we have full analogy with Poincare lemma, so we don't have to reinvent wheel. We only need to use it. And we have additional bonus, which is very deep. I would say it is very deep for physicists. So in our reasoning, we get this homotopy formula. So we have this equation of motions or Euler form. We apply homotopy operator, and we get Lagrangian, but sorry, action. But this action is defined up to some constant, which this constant is depends on the center of the homotopy. So on some special say trajectory of the system, because the center of the homotopy is some kind of trajectory. Okay, and so we understand now why the action or Lagrangians are defined up to some constant. This constant can be infinite, of course. In physics, there is plenty of infinite constants which you modify, by which you modify your action. Yeah, for example, in renormalization. So this is not some trick, but it depends on what kind of center of homotopy you take to inverse your equations of motions to get action. So if you follow this path, then the question is, what's more fundamental? If equations of motions are more fundamental, or if action is more fundamental, or Lagrangian is more fundamental? Yeah. So in these terms, you see that the equations of motions which sit in this F are, I think, are more fundamental, because action is something like potential for this F, or for equations of motions. So it is like in electrodynamics. You have fields which are electric and magnetic fields, or F mini tensor, and sometimes you can find potential, yeah, for this, and potential is defined up to some constant. And this is exactly the same situation, but instead of fields like electromagnetic fields, you get equations of motions, and instead of potential, you get action or Lagrange. Yeah, so that's the correspondence between these two. So you have like translation table. So in electrodynamics, you have potential or force, and or classical mechanics, you have force, which should be potential. So this condition of Poincare lemma, so it's closed, is exactly the requirement that the force is potential, and then locally you can define potential for this force, but this potential is up to additive constant. And it's normal, and this constant can be also infinite. Like okay, maybe there is plenty of places in physics where there appears some infinite this reference level for potentials. And in our approach here, what I try to convince you is that you have equations of motions, which I think they are basic, but it's a philosophical question. But anyway, you have some equations of motions, and if they are potential, so if functional exterior derivative evaluated on these equations, on Euler form, which has these equations, is 0, so that's the condition of potentiality for equations, then locally, at least locally, sometimes globally, but in this framework locally, you can inverse these equations or this exterior derivative, and you get action functional up to additive constant, which of course then can be also infinite. But anyway, it's some constant. So action is defined up to some constant, and this is because equations are fundamental things from which we start, and we use homotopy formula to invert these equations to get action. That's all what comes from this approach. So the question is a philosophical question: is what is more fundamental, if it is if they are equations of motions more fundamental, or the action? Of course, there is plenty of physicists which claim that action is more fundamental because you can calculate more and it's easier, but it's the same situation as between force and potential. Using potentials, you get scalar equations or conservation of scalar quantities, which is easier to manipulate than forces. But I think the equations of motions are in this approach more fundamental. But of course, it's good question for discussion, like when you drink a wine with some colleagues. It's not, I think, not so physical. But anyway, let's apply these rules to some basic examples. First example is classical heat equation. So heat equation is here inside this bracket, and I multiplied it by delta U, which gives you this Euler form for this equation. So, yeah, of course, this ut and uxx are jet coordinates in this setup. They are not real functions. They are not derivatives of functions. They are jet formula. And of course, there is integral sign, and you can evaluate it by pulling it along the Cartan distribution and plugging here some specific variation. And this single form corresponds by integration by parts in many ways to this form. So, for example, this is this original Euler form. This form comes from integration by parts of this t to, or switching this t to, or plugging this t to this delta u. So this here is t, and the minus sign from integration by parts, and this uxx term is unchanged. The second or the third formula is by integration by parts of 1x. So here is ux only, minus is from integration by parts, and delta ux is here because of integration by parts, and so on. So you have plenty of possibilities. So it's some kind of combinatorial way. But if you assume that Lagrangian is of this form, and you know that how the homotopy formula works, then from all these possibilities you pick only two, because they restore Lagrangian of this form, which contains only first derivatives of t and x. So you have this form or this form, because here is u and ux. Okay, and now if you want to check if it's variational, of course it's not, because we know this already, but because heat equation has no Lagrangian, but let's check it. So if you take functional exterior derivative, then this term, gives you delta ux, wedge delta ux, which is 0, and the same is here. So what is left is such term, so exterior derivative of this first term, and this first term spoils you variationality. So you can trace which exactly term in equation is problem in creating Lagrangian for the equation. For a heat equation is exactly this ut term, because this term doesn't vanish after taking functional exterior derivative. Yeah, so it's very nice tool for checking variationality. You can trace each term in the equation and check if every term is variational. Of course, sometimes you can integrate by parts and mix these terms in some sense, but in such simple equation, you can exactly pinpoint which term is abstraction for formulate this equation as Euler and Lagrange equation. Okay, so this equation as it stands has no variational formulation because the exterior derivative of this form is not zero. It's exactly
actually, Radoslav, the same comment applies as in Helmholtz. You can still multiply this Euler form with some equation, and then it's not clear that the functional derivative it should be close. I mean, you can still make changes, and the check is not sufficient.
Yeah, precisely. Yeah.
So I mean, it's true actually. I think that in the heat equation there is no Lagrangian formulation, but you actually have to do more than what you just did.
Yeah, precisely. That's what I write it as it stands. So only for this form. If you change it, then probably it may be, but we know it's not.
We don't know. Yeah,
it might be.
I think it's not, because else somebody would probably have written a paper about it. But it's certainly not known.
Sorry. Yeah, precisely. That's very good comment, and we will. I will show you that you can change equation and make it from non-variational to variational. That's
sometimes.
Yeah, sometimes.
But not in this case.
Yeah, precisely. Yeah, but anyway, you are right. What I showed here is that this precise form of this equation, without any alternation as it stands, is not variational.
Yeah.
That's what I showed here, and nothing more. Nothing more. So it's not too general,
right?
Because you always can change this equation and check again. But we will go to this.
In fact, it's the UT that's the problem, as you showed.
Yeah, precisely. That's the term which is problematic. And
right, but of course we know there is a simple solution in this case. Which we just have to make U complex. Then of course this is the Schrödinger equation.
Yeah, precisely. Or there is also another approach which goes to the same direction, which is exactly adding one more field, not necessarily complex. It's called superfield or super.
Oh, sure. Yeah, that's more or less the same. I mean, because complex is also adding fields.
Yeah. So that's. It's good that we have this discussion, because this equation is very simple, but yet it doesn't have Lagrange form. So some physicists, I have some arguing with some very devoted physicists to the action principle that everything fundamental should be variational. So from their point of view, this equation is not fundamental. Well, it's heat equation, so it describes some low level propagation of heat. So probably it's some effective equation. So here it agrees, but we will see that, for example, for forced harmonic oscillator, it doesn't agree. It has a Lagrange. So it's quite nice. Anyway, okay, some unstable connection, but I hope we made it. So we have now forced.
That's by the way why I have no camera, because my connection is unstable.
Okay. Okay. So forced harmonic oscillator. So form is something like this: UTT plus U is times delta U. Delta U is from this switching to the one forms, and we have equivalent formulations by integration by parts. So this is original one, and then we can take this T and put it on this variation. Then we have additional minus and so on. And second integration by parts takes this double T to this variation. Okay, anyway, if we look Lagrangian of the first order, so depends on U and UT, then we get from these possibilities, we pick only the middle one. So we have this Euler form, and now we know what to check. We have to check if it's a functional exterior derivative vanish. So if we compute it, Then from this we get 0 because it's antisymmetric and we multiply the same terms. And sorry, here shouldn't be this u. That's mistake. So delta u, wedge delta u, and this is also 0. Yeah, so we get the 0, and we can use homotopy operator to restore the functional. And this is exactly this Lagrange functional or Lagrangian in this bracket, but it's minus Lagrangian, minus usual Lagrangian. But anyway, it's the same, plus minus. So we restored full Lagrangian from this equation without any problem. And we also check that this equation as it stands is variational. Okay, so now let's go to multiply problem. So as Klaus said, maybe the equation is not variational by this procedure, but maybe we can alter it a bit to make it functional. So help him or it to be functional. So the simplest approach is to start from the equations and then make linear transformations of this between these equations. Or for single equation, we multiply it by some multiplier, let's say integrating factor, which make it variational. But there is a problem with this. If we have more equations or more variables, because for example, we have this term x two dots. And if you consider Lagrangian like x dot dot y, then it can result, this term can result from the term x two dots delta y, which is proportional to delta y, but it also can result from x dot squared, which after this functional external derivative gives you this, which is the term proportional to delta x by integration by parts. So if you integrate by parts, then you get this term, which is x two dots, but times delta x, which is proportional to delta x. So we have two alternative, I'll say, terms, x two dots y and x dot squared, which can give the same term x two dots in equation of motion. Yes, so we don't know how to multiply this a alpha by which variation, if it can be delta y or delta say x, to get to restore this functional one form. So that's the problem also in this original approach, which uses Helmholtz conditions. And our approach, this functional exterior calculus, solve it. So we have this non-uniqueness. We don't know how to multiply these equations by delta variable. And but this functional exterior calculus solves this problem completely. So what's the solution? So we have these equations of motion, like from alpha equal 1 to r. R is some maximal number of these equations, and we have variables u1 to ur. And now we don't know if a1, for example, comes with delta u1. It can come with delta r or delta 2, u2. So we introduce some mixing matrix, which mix or create all possible multiplications. So in standard multiplication problem, you have this matrix U and multiply these equations and plug it into Helmholtz conditions. But still, we have this problem. We don't know how to associate delta variable to the equation. And in our problem, we construct a one form. So we have to also multiply by this delta U1 to delta UR. And this matrix A mix all, or create all possible connections between delta U and equation by this multiplication by these coefficients of the matrix A. So if we create this general form, then these conditions rho acting on this form evaluated on the equations equal to 0 is exactly conditions for these coefficients inside the matrix. So if we can solve these equations for these coefficients, of course you can assume that these coefficients are constant or depends on some functions and so on. So it's your imagination what would you do, but if you can solve this condition for these coefficients of the matrix, then you can provide multiplication factor or multiplication matrix for. So you can solve or you can check if there is linear transformations of original equations to make them variational.
But Radoslav, couldn't we be more general? I mean, couldn't they, instead of just multiplying, couldn't we also use some differential operator?
Yeah, that's the very good question. You are one step ahead my presentation. So yeah, so if you use Helmholtz conditions, so up to my knowledge, that's all you can do with Helmholtz conditions. And it's in case of functional exterior calculus, it's very simple condition. So and you cannot do, for example, nonlinear transformation because Helmholtz conditions. Well, maybe I'm not expert, but I couldn't find any example of nonlinear transformation for equations to get you variationality to make it them variational.
What do you mean by nonlinear? That these a's are just numbers?
No, they are equations. They are equations. So they are some formulas on jet space. So for example, like this one.
No, I meant the factors of the matrix you're multiplying it with.
So
there are also functions on jet space?
Yeah, they can be in general case. Yeah.
Okay.
Yeah.
Okay.
But still they are linear. This is linear change of the equations.
So I guess there's both linearity, which can be abandoned, and there's also differential operators on top of it.
Well, more maybe different way. So instead of linear transformations, you can generalize it, and I will show you it soon. That you can use nonlinear functions, and you can do the same. And
yes, but still on top of nonlinear, that you also need differentiable to differentiate.
Yeah, precisely. But you know how to do it because you defined this functional exterior derivative. And so the difference between Helmholtz conditions and this approach is that Helmholtz conditions are fixed system of differential equations, which you have to plug in your equations and you get something. And in this case, you have more flexibility because you know how to differentiate functionals, and you can mix these functionals in every possible way. And after
sure, but this is not the. I think it still doesn't address. So what I'm basically saying is that you should also include in the column of E, the equations of motion. You should also include all differentiated equations of motion.
Yeah, that's a good point. I didn't consider this, but yeah, you are.
So you should extend to get what I want with differentiation is that you should include in the column also all possible differentiation of the equations of motion, and then multiply with all linear combination, and I guess possibly non-linear.
Okay, yeah. That's a good point. I didn't consider it to be the case, but yeah, it's nice comment. I have to think it over, but probably well, I'm not sure, but yeah. Good comment, very good comment. I didn't think about it, but anyway, if you stay in your original equations without any prolongations to higher jets or differentiating it, then the problem is simply multiply equations and plug them to Helmholtz conditions. And in our approach, you construct a functional one form which also doesn't care about the order of this delta U multiplication by the equations, and the condition for the solving of this matrix is to solve this equation. So it's the same as in the exterior calculus for functions, but in functional way in this case. Okay, so let's let's apply this. As you know, that the single first order differential equation, ordinary differential equation, has no Lagrangian. It's not variational. So this equation, you can check it as before. It's very simple calculus. It's one line proof. Of course, if you use Helmholtz conditions, it's a few lines proof, but in our calculus, it's only one line proof because of this term. This term is the same as in heat equation, and it gives you the problem or abstraction to variationality. But the question is, if we can multiply by matrix, in this case, we have one equation, so matrix is a simple scalar, so this function G. If you multiply by this Euler form of equation by G, if it's variational. So the proof is very simple. So you take this variational derivative, evaluate on the equations, and you get that G times delta x dot wedge delta x must be 0 if it is variational. And from this condition, you cannot vanish this wedge product. So you have to vanish G. So only when G is equal to 0, then there is variationality. But if G is 0, then you have no equation. So, in multiplication by integrating factor is not helping here. So this equation is still non-variational for this multiplication. Okay, so let's consider now another problem. It's called damped harmonic oscillator. So you have this harmonic oscillator with this term which is proportional to t. So B is, say, some constant, which is this force, friction. And you know, because of this term, that this is not not variational as it stands. But maybe if you multiply it by lambda, this is this integrating factor, maybe you get Lagrangian for this. So let's try. So we construct this Euler form for this. It is like this, and there is plenty of possible ways to do it. But if you restrict it to Lagrangian, which depends on u and ut, then you pick one preferred candidate for this. So if you take this Euler form and make this exterior functional derivative, then you get something like this, which is 0 when you fulfill this equation that this lambda t is equal to b lambda, because these two terms are the same, so you have to cancel the say coefficient of this double form or these two form. So you have to solve this equation. Lambda t, derivative of lambda with respect to t, is equal to b lambda. So this is a simple equation. You can solve it at once. So the solution is exponent, and c is some constant. And now substituting this lambda to this original Euler form and applying the homotopy operator, you get, so we have this. Applying homotopy operator, you get exactly Lagrangian. So this lambda is this exponent, and here is Lagrangian for harmonic oscillator without damping. So this damping is generated by this lambda factor, and you'll see it at once using this approach. So returning to this fundamentality of action, you see that no forced harmonic oscillator is not fundamental, because friction forces are not fundamental. They are fundamental on the microscopic level, not on this average level. But still, you get Lagrangian and action formulation of this theory. So yeah, it's funny. Okay.
Just a small comment.
Yeah, please.
It's a damped, not dumped.
Yeah. Sorry. Yeah, that's a good point. It's the different words. Yeah. Okay. Maybe I have also one comment. So you can. I've seen a paper about quantization of this damped harmonic oscillator. So yeah, it's also considered in quantum mechanics. Okay, and now what Klaus wanted to see, so nonlinear transformations. So using this calculus, you can also consider the most general way of transforming equations before you check its variationality. So I call it nonlinear transformation problem because I couldn't find any other name, because I don't think that using Helmholtz conditions you can consider such problems. But this is the more general approach for finding variationality or imposing variationality. So you have some system of differential equations, and you have some set of variables which these equations depends on. And now you can construct. You select some functions. You don't specify. You say that there are some maybe there are some functions f alpha. The number of these functions, the multiplicity of the functions is it depends on you how many they are. And you construct Euler one form in some specific way. So you take these functions f alpha. These functions depends on jet coordinates, but instead of this, you plug as coordinates this original equation. So you non-linearly transform these differential equations at the beginning, and then you multiply by this delta u beta. you don't have to carry about the order of this multiplication by this delta u, because these nonlinear functions also mix, like this matrix mix the order. So f is very general set of the functions. And now, if you have this Euler form, the condition for variationality of this altered equations is the same. So exterior derivative, functional exterior derivative acting on this form at the equations must be equal to 0. And if it's fulfilled, then you get conditions for this f. So you can restore this f. And one simple, okay, and this of course generalize linear multiplication problem. So multiplication by matrix, because f is non-linear in general case, but it can be also matrix which multiply linearly these equations. Okay, so maybe one simple example just to convince you that everything works. So let's consider this the simple system of two equations, x dot equal to 0, y dot equal to 0, which has solution on the plane which are straight lines. Okay, so let's assume that we want to check if it's variational by using some nonlinear functions. So let's pick some f and g functions, which assume that they are C infinity on R2, because we want to differentiate them. So we assume that they are quite smooth. And now construct this Euler form. But these equations are inserted here as variables. So f depends on x dot and y dot, and g also depends on right-hand side of first and second equation. And these functions, because epsilon is one form, they should be multiplied by delta x and delta y. Okay, so now we know what to do to check variationality. We have to check if 0 is equal to a functional exterior derivative of this Euler form. So we calculate it as in ordinary exterior calculus. Of course, everywhere there is integral sign, but I don't write it because there would be a mess. That's why I omitted this integral sign at the very first place. Okay, so the first condition is that this term should vanish because it doesn't match any other term, because it contains only x's, x and x dot. And there is no other term which contains only x's. And the second term, the last term here also contains only y dot and y, so it also must vanish. So this is the first condition, or the first two conditions, which gives you that f depends only on y dot and g depends only on x dot. Yeah, nothing more. This is exactly this condition, and these two middle terms can be combined because they contain y and x, and the same here. Well, there is dot on in the first term on y, in the second term on x, but you can integrate by parts and switch or put this dot on the second term. So let's do it. So by integrating by parts, the first term, you get this additional term with y two dots, and this one. And now from this, because this term delta x delta y is not present here, because here we have delta x dot and delta y and delta x dot to delta y. So this the second term in the bracket and the last term can be combined to make some more complicated equation, and the first term must be vanished. So we have that this coefficient must vanish. And because we assume that y to second dot is not always 0, then this first term, the second derivative of f with respect to jet coordinate x y dot squared must be 0. So from this we get that f depends linearly on y dot. A is some constant, some linear, well, constant. Yeah, I think constant with respect to y dot. So you can. Well, no, sorry, it cannot depend on x dot because of this condition. Okay, so it's true constant. And the second condition comes from a combination of this second term from the bracket and the last term here. So you get this equation, and from this equation, knowing that f is of this form, you get that g dot x dot is minus x dot. So as a result, you get that your Euler form, after plugging this f and g, is as follows. So it's constant times y dot d delta x minus x dot delta y. And probably you know what does it mean. So, applying homotopy operator, you get this Lagrangian, and as you know, or you are a physicist, yeah, of course I am also, but this is this term which couples constant magnetic field to the velocity. Yeah, it's cross product of vector potential of this constant magnetic field pointed in z direction with velocity in the plane. So yeah, it has very it's well, this example can be extended to the whole electromagnetic field, but in this case it shows that that lines that particle or maybe don't go to this, but it is connected with electromagnetic interaction. Well, constant magnetic field perpendicular to the xy plane. Okay, as a summary, we see that, or we have seen that variational calculus can be made simple application of Poincare lemma, or at least some kind of exterior calculus, but on functionals, not on functions. We also have seen that Helmholtz conditions are, well, complicated, at least for me, and they can be replaced by Poincare lemma, well, functional version of Poincare lemma, which is called Helmholtz-Weinberg theorem. So we also have seen, using this say analogy, that Lagrangian is for equations of motion something what is potential for the forces, potential forces, of course. So Lagrangian is something which is like second, I would say, second level quantity, or action is second level of quantity for the equation of motions. So from equations of motions you get Lagrangian, and yeah, for the opposite direction is obvious by Euler-Lagrange equations, but this calculus suggests that maybe equations of motions are more basic, because yeah, not every equation has its Lagrangian. Okay, and Poincare lemma says when it is possible. And the also very important thing, which is connected with my previous papers about this homotopy and this exact, anti-exact forms and so on. So it says that this Lagrangian is something like functional, corresponds to the something which is called anti-exact differential forms, but in functional way. So these are functions which depends on this choice of the center of the homotopy, and they vanish at the center of the homotopy, and of course they are in the image of the homotopy operator. So that's the specific condition for the Lagrangians, which comes from equations of motions. Okay, and my future plans are go to quantum world with this theory. You see that computations are very simple here. As a physicist, you are expected to know what is exterior calculus. So if you know this, you can do all these calculations also in a functional approach and play with this very simple, without knowing even what is Helmholtz conditions, because this calculus provides and yeah, so maybe one interesting or deep comment, that this approach is equivalent to Helmholtz conditions because it bases on this Helmholtz-Weinberg theorem, but it creates you Helmholtz conditions which are suited. They are not very general Helmholtz conditions which you get from some book, but they are fitted for this specific problem. So that's why you don't get plenty of terms, but you get only these terms which are particularly important in this case. So full set of Helmholtz conditions is reduced to the specific problem, and that's why the calculations are very fast and very simple in this functional exterior calculus. That's the correspondence between these two. Okay, so thanks for my supporters and sponsors. And about literature, because I think if someone is interested, maybe want to know more. So if you want to see this functional version of Poincare lemma, then it's better to go to Weinberg book. It's well, it's very difficult to get it from the library because it's very old book, but you can download it by free. It's freely available from some open library. But it's not I think it's okay. Not you don't break the law when you download it. So because the book is very old. So this is very nice course on functional analysis in real Banach spaces, and it contains as one of the theorem this Weinberg theorem. If you want to know how this calculus was formulated for variational derivative, then you should look on these two sources. The first one is the paper, which was well published in 1808, previous century, and it contains the definition of this calculus in terms of variational derivative, not this functional exterior derivative, which is more general, but only variational derivative. But more or less, they are quite. There is a big overlap with what I presented. And yeah, and the second source is also connected with this professor. And it is a book about the geometric method in physics. It's a very nice book. It's more like a tutorial, not a strict mathematical book, but it's very, I would say, informative. So I very recommend it for reading. It has plenty of subjects inside, so it's a very big book, but it's very nice. I like it very much. And this chapter, which treats about this function, about this variational exterior derivative, it's in chapter 20. If you want to fix this or pinpoint this chapter. Later, when I put this paper on arXiv, or this draft on arXiv, I have comments from some of my colleagues that they try to do something similar, and this is one of the paper which treats about similar approach, that it tries to make functional or derivative, exterior derivative of the functional on the jet space. So it's in the same direction, but they stopped not going to this inverse problem. So it was like, if they go farther, then probably I wouldn't. There will be no work for me because they would finish, but they stopped before. So my work is some kind of extension of the result. And if you want to learn more about the Poincare lemma, of course, there's plenty of literature, but of course, I recommend my papers. Well, the first one was already published. It is basic stuff about Poincare lemma and applications to some nice problems in physics. And the second one, draft, is what I presented last time here about this connection of Poincare lemma with Clifford algebra. And this, as I said, Lagrangian or action functional is the same as, in these terms of Poincare lemma for ordinary functions, is the same as anti-exact forms. So it's functional version of anti-exact forms, functional forms. So yes, so everything is closed. So because every basic physical equation can be formulated in terms of exterior calculus now, and Poincare lemma can solve it locally at least. And now we add here that every variational equation can be also treated in similar ways using some analogy of Poincare lemma, and these anti-exact forms also appear in this framework. So as you see, the only thing which physicists can learn, if you have very small amount of time to learn physics, then what you have to do is to focus on exterior calculus and Poincare lemma. That's all you need. Well, it's of course a joke, but more or less locally to solve some physical problems, this is the tools which you need. Okay, thanks. I don't know if you have time, because I have also some small backup, but I think I already talked by almost 2 hours. So I don't know if you are exhausted by me.
Yeah, we don't really set a specific time for the talks, so you're fine. So, but now we can have a discussion or questions, and then if people want, we can go to your backup, I guess.
Yeah, sure.
Yeah. So I have